Build a simple recommender using matrix factorization. By the end, you will have a tiny factor model, a working recommend function, and a way to measure fit with RMSE. RMSE is root mean squared error, a measure that averages squared prediction errors and then takes the square root. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Matrix factorization matters because it directly optimizes reconstruction error, which often correlates with recommendation quality. It trades off memory for compact latent matrices and some latency for dot product scoring. At small to medium scale, it is fast and accurate. And on datasets with thousands of users and items, you can see clear gains over naive averages. The intuition is simple. We approximate the rating table with low-rank user and item vectors. It shines when users share common preferences, and when ratings are dense enough to learn patterns. It struggles with cold start and with features that are not collaborative. We will keep things tiny and clear so the effect is visible. We will build a tiny ratings matrix, compute a global mean baseline, factor into user and item vectors, recommend an unseen item, test simple regularization by shrinking a latent dimension, and finally clamp predictions into the rating range. Now we build the tiny dataset and baseline. This snippet builds a tiny ratings matrix and computes the global mean rating. It creates an array called R, where zeros mark unknown values, and it builds a Boolean mask M that marks the observed entries. The expression that filters R with M picks only the known scores and averages them to produce a single baseline value called mu. That global mean is a simple fallback predictor when no other signal exists. It is a neutral starting point for later factorization. The printed mean gives a quick sense of the typical rating level in the toy corpus. Next, we set up the factor matrices and test fit. This snippet factors the matrix with tiny latent vectors and measures RMSE on observed entries. It defines U for user vectors and V for item vectors so that their dot product via NumPy dot produces predicted ratings P equal to U times V transposed. The mask R greater than 0 keeps the error calculations focused only on entries we actually observed. The snippet squares the errors, averages those squares over the known count, then takes the square root to compute RMSE. These example factors are chosen to match known ratings closely, so the RMSE is very small and illustrates how factorization can reconstruct observed data precisely. Now we pick a recommendation for a single user from the predictions. This snippet recommends the best unseen item for user 0 using factor scores. It reuses U and V to compute the full prediction matrix P via NumPy dot. For user 0, the expression that checks R0 masks items the user already rated and substitutes a very low value for those entries to avoid recommending seen items. Then the argmax function finds the index of the highest remaining predicted score. This produces a single clear recommendation target without extra filters or tuning. The printed tuple shows the chosen unseen item index and its predicted rating for user 0. Next, we demonstrate simple shrinkage on one latent dimension. This snippet shrinks the second latent dimension to show how regularization alters error. It scales the second component of the item matrix by 1/2, so that the second latent dimension contributes less to the predictions. New predictions come from the adjusted item vectors multiplied by the user vectors via NumPy dot, and the snippet recomputes the error only on the entries we observed. Shrinking a latent component is a form of regularization. It can reduce overfitting to noisy entries, but will often increase bias. The printed RMSE exposes that trade-off by showing how the fit worsens or improves depending on the shrink factor. Now we clamp outputs and list candidate scores for another user. This snippet clamps predictions into the valid rating range and lists user 1's unseen item scores. It computes factorized predictions P and then applies NumPy clip to keep outputs between 1 and 5, so they stay within the original rating scale. The code finds indices for items that user 1 has not rated, and produces a compact list of those indices paired with rounded predicted scores. Tight clipping prevents extreme values but can compress score differences. Looser clipping preserves spread, but risks out-of-range predictions. The printed list gives ready-to-act candidates for user 1. Recap in 3 crisp points. Matrix factorization approximates the rating table with low-rank user and item vectors. Use it when collaborative patterns exist and you need compact, fast scoring. Caveat: it needs observed ratings to learn and struggles with new users or items without side information. Next step: tune the latent dimension and the shrink factor while tracking RMSE and recommendation hits on a larger validation set to balance bias and variance. If practical recommendation systems help your projects, subscribe and watch the rest of the IR series.